Okay, hello again. Hello. So today we're going to talk about the next unit, and in the next unit we're going to look at techniques for finding the derivative. So we already have one technique, and it's called the power rule. So let's start by reviewing what the power rule tells us. The pattern is if the function can be written as x to the n, the derivative can be found by, it looks like, pulling the power down to the front, and then the power on the derivative is going to be 1 less than the exponent on the original function. So an example. An example is that the derivative of x cubed is equal to 3x squared. And I'll do some more examples here in a minute, but before we continue, I wanted to talk real quick about a couple of alternative ways, alternative notations for writing the derivative. So we've used this one a lot, right? F is equal to this, f prime of x is equal to that. Here are some other notations. So there's what's called a differential operator. So it's a way to say, here, take the derivative of this, and it looks like this. And we say d dx, so d dx of x cubed. So what this means is take the derivative of what comes after this with respect to x. So I would write d dx of x cubed. Oh, they're telling me to take the derivative. Okay, so this is equal to 3x squared. Okay, so if you wanted to use this kind of notation to take the derivative of like 5t to the 7th, you would say d dt, 5t to the 7th, and what would you get? Well, the 7 brought down to the front would give you 7 times 5, which is 35, so 35t to the 6th. So we're talking about the power rule over here, but we're also talking about this alternate way to talk or to write, like the act of differentiation. So that's one thing that I wanted to be sure to go over with you. Here's another thing. If you have not f of x is equal to whatever, but y is equal to whatever, you can use this same idea to talk about the derivative. So if we have y is equal to this, and I'm just going to write real quick that means that y is equal to x to the 1/2, right? Because a square root is the same thing as a 1/2 exponent, right? To write the derivative of this thing, if you d dx over here, and you d dx over here, what you'll end up with over here is 1/2 x to the negative 1/2, right? If you bring the power down to the front and then subtract 1 from the power that you have, you'll get this. And to d dx the variable y, it's written like this. If y is equal to this, dy dx, the derivative of y with respect to x, is written like this. And this notation has a name. It's called Leibniz notation. And I think I have a little info about Mr. Leibniz. Suppose you have y is equal to 1 over x squared, and you want the derivative of this thing. First, I would want to write this as x to a power so that I can use the power rule. And I just wanted to mention that there are some sort of shortcutty kinds of things. So I've seen people use this. It's not really technically correct. It's not incorrect, but like if you were going to write a paper and submit it to a math journal, and I know that you're all avid math journal readers, right? They probably would not use this kind of notation, but everybody knows what it is. And so it's okay with me if you write this. I tend, when I type things up, to either use this kind of notation or this, but sometimes when I'm doing work on the board or if I'm just doing some work really quick, I'll write it like this. So this is going to be -2 times x to the -3, right? If I bring the 2 down to the front and then subtract 1 from the power, I'll end up with the power of -3. Another sort of shortcutty thing, to do this same thing that I'm doing here, sometimes I just go like that. I just want to take that thing and prime it. And again, that's kind of an informal way to write it, but I just wanted to make sure that you knew that all of these are acceptable ways to talk about and write the act of differentiation, okay? The other elementary rule of differentiation that we want to look at today is what to do with an exponential. So let's look at e to the x. So what is the derivative of e to the x? Well, there's a couple of ways that we could look at this. One way is to look at the graph of e to the x, because we know how to graph a derivative based on the graph of the function, right? So this is the graph of e to the x. So if I wanted to graph the derivative of e to the x right down here, I could do that by looking at the slopes everywhere. So I see a couple of things here. One is that the slope is always positive, right? Because the curve is always going from lower left to upper right. So the graph of the derivative will be above the x-axis, right? I also see that the slopes are increasing because as I continue around the curve, the slopes are getting steeper, and that means that the value of the slope is getting bigger. So it turns out that the derivative of e to the x, its graph looks a lot like the graph of e to the x, right? Everywhere positive, and slopes are getting bigger. All right, so maybe the graph of an exponential is also an exponential. All right, that's sort of a good intuition. Another way that we can explore the derivative of e to the x is to use the definition. So if you remember, oops, excuse me. Sorry about that. That was the bike shop. My bike is fixed. Yay. The definition of the derivative, the limit of right, is this. So if we try to do this to e to the x, we need f of x plus h. What does e do to its input? It takes its input and, what is e? What does f do to its input? It takes its input and uses it as an exponent on e. So f of x plus h is e to the x plus h. Okay, so So when we plug all the pieces into the limit definition, we get an expression that looks like this. And now I'm going to do something and tell me if it's all right with you. So what I did to get from here to here was I took the fact that when you're multiplying two quantities together and you have the same base, you add the exponents, right? So if I had this times this, I could combine them and I would get this, right? Well, if you have this, you can go the other way, right? And pull them apart so that it looks like this. And the reason that I would do this is because now I see that I have an e to the x that I can pull out. So, I was able to get the e to the x out of there, but I still am not able to plug in h is equal to 0. So I need to know what this is equal to when h gets really small. So I don't think algebraically I'm going to be able to do anything with this, but I can check out the values of this thing on the calculator. So let's do that.
Here's the calculator, and we've entered the expression into the y equals screen. And what we want to do is we want to look at the values of this thing as x gets very close to 0. And so if you pull up the table, I've already punched those quantities in, and we can see that at x is 0, the expression is undefined, but as we get close, either from the left or from the right, the values of the expression appear to be getting closer and closer to 1. So that's the value of the limit.
Okay, so the happy news is that the derivative of e to the x is equal to e to the x. So that's a super nice result, one that we intuitively might have guessed. Yeah, so good. What if we change from e is equal to like 2.718 something? What if we change the base from e to 2? How does any of this change? The graph looks almost identical. It looks like this. So I would expect the derivatives graph to look a lot like the graph of f. So we still have that. If we come over here and I change these e's to 2's, now what we need to look at is the values of this thing as h gets really close to 0. So let's go back to the calculator and see what we get here.
And so here we go again, this time with a base of 2. So if we look at our same table of values, it's not quite so clear this time what's going on. The limit seems to exist because the closer we get to 0, the closer these values are getting to each other, but they're not getting closer to a recognizable number. So let's see if I can help you to see what the number is. We just want to pull up the value of that thing at a place that's very close to 0. So I'll put in something like this. So that's the number that we get. So what number is this? It's very close to the log of 2. So actually, log of 2 is the value of the limit.
The result is that the derivative of 2 to the x is equal to 2 to the x times a constant, and the constant happens to be the log of 2. And it actually always works like this. So the derivative of 3 to the x is 3 to the x times the log of 3. The general case is written like this. The derivative of a to the x is equal to a to the x times the log of a. So, yeah, those are our elementary derivative rules. Let's look at an example. So how about this one? Take the derivative of 4x cubed plus 5x to the negative 2 plus 4 to the x. This is a power rule problem. This is also a power rule problem. This is an exponential. The pull the power down to the front thing does not apply to the exponential. You can only do that when the x is here, when the x is in the base. If the x is up here, then we have to use the rule that we just looked at for the derivative of an exponential. So putting it all together, we get, if we pull the 3 down to the front here, we get 3 times 4, which is 12. So 12x, and the power on the derivative will go down to 2, right? For the next term, if we pull the negative 2 down to the front, we get 5 times negative 2 is negative 10. And when we reduce the power by 1, be careful, it goes down to negative 3. And then the exponential on the end, the derivative of an exponential is the exponential times the log of the base. So this thing on the end here is going to be 4 to the x times the log of 4, and that is the derivative. Find the equation of the line tangent to the graph of 2 minus 3 to the x at the point where x is equal to 1. So let's get a picture of this thing. So 2 minus 3 to the x is going to go down. Yeah. So the graph of the function looks kind of like this, and we're looking for the equation of the tangent line here. Do you see it? Okay, so I can see that the slope of the tangent line is going to be negative and kind of largish, bigger than 1 anyway, and that the place where the tangent line hits the y-axis is going to be positive. So I can see those two things just from the picture that I've drawn here. Let's do the work. So for the equation of the tangent line, we need a point on the graph, and we need the slope of the line at that point. To get the point on the graph, well, I gave us the x part of the point, and so we just used the function to get the y part of the point, right? So the point is 1, g of 1. And what do we get if we replace the x with 1? We get 2 minus 3, negative 1. The slope is what we get when we take the derivative and then plug in x is equal to 1. So when we differentiate this, the derivative of 2, the derivative of a constant is 0, right? And the derivative of 3 to the x is 3 to the x times the log of 3. So g prime is negative because of the negative right here. 0 minus, then we'll get 3 to the x times the log of 3. And the slope at this particular point, we want to evaluate this when x is equal to 1. So g prime of 1 is negative 3 to the first times the log of 3. So negative 3 logs of 3. And this is about equal to, oh, I don't remember. Hold on, let me get my calculator. Logs of 3. About 3.3-ish. It's about 3.3. Negative 3.3-ish. The scientific way to write this is 3.3-ish. That's a little joke. So if we put it all together, the equation of the tangent line is y subtract the y part of the point is equal to the slope times x minus the x part of the point. So you get y plus 1 is equal to negative 3.3x plus 3.3, and if you subtract 1, y is equal to negative 3.3x plus 2.3. And let's look at the graph of the function together with the graph of the tangent line. And that will be tremendously gratifying.
It's kind of fun to see that the work that you're doing makes sense and is doing what you say it's doing. So we just want to look at the graph of the function that's in y1, and then here's the expression that we've come up with that gives the equation of the tangent line. So I've set up the window, so we should be able to get a pretty good view of this. So here comes the exponential. Oh, and there's the tangent line. That looks nice.